We've solved all sorts of geometry problems involving graphs using calculus. But now that we have parametric curves, we can solve the same sort of geometric problems for parametric curves that we did with graphs originally. The solutions will look a little different, but we'll use the same ideas. And there are some key tricks for turning what we know about graphs into techniques for solving the corresponding problems about parametric curves. So let's have a look at some examples. So let's find the equation for the tangent line to this spiral parametric curve, t cosine t, comma t sine t. And let's find the tangent line at this point, pi over 4, comma pi over 4. So if you graph this parametric curve, it turns out that it looks something like this. Okay, and it keeps going around and around as t increases more and more. And there's a point here, pi over 4, comma pi over 4. Okay, and there's some tangent line. It's a little bit hard to know what direction the tangent line might point because I haven't drawn this graph very accurately. You know, maybe it looks like this, or maybe it's more like this. Maybe it's vertical, or maybe it's like that. It's hard to tell. But if this were a function, right, if this were y as a function of x, then we would say that the slope of the tangent line is just dy dx. Okay? Well, y isn't a function of x, but actually the slope of a tangent line is still dy dx, even though this is a parametric curve. Because remember, sort of, if we zoom in on a part of the graph here, on the part of the graph near the point where we're interested in, right, dy is some small vertical displacement away from this point, and dx is some small horizontal displacement, and the ratio of these is the slope. The fact that these displacements came from a parametric curve instead of from a graph somehow doesn't really matter. The derivative we're after is still dy over dx, even though dy and dx are coming from a parametric curve. So we still want to compute dy dx. But how, we don't have y as a function of x, and we aren't likely to get it. So how can we use this parametric description to calculate dy dx? Well, remember that another way to write these parametric equations is that x is t cosine t, and y, I'm going to leave a little space here, y is t sine t. But we need to know dy and dx. Well, we can calculate dx, and we can calculate dy, right? Just take differentials on both sides of these equations. So this is very much like when we did a u substitution or a trigonometric substitution. After we wrote down our substitution equation, we needed to calculate differentials. It's the same thing here. So to calculate dx, that's going to be the derivative of x with respect to t times dt. So the derivative of x with respect to t, well, just take a regular derivative, treating t like the variable. We're going to get, so we have to do the product rule, so we get cosine t plus a minus, I guess, because when we differentiate cosine, we get minus sign. So minus t sine t. And then don't forget this dt right here. Okay, and then we'll do the same thing for y. So again, we have to do the product rule. So we get sine t plus t cosine t times dt. So now we can take these expressions for dy and dx and put them into this ratio, right? Put dy in the numerator. So that's sine t plus t cosine t all times dt over dx, which is cosine t minus t sine t times dt. Okay, now we can simplify this because we have dt over dt, but dt is 0, or not 0, 1. So the dt's are gone. And our expression for the slope, dy dx, is now sine t plus t cosine t over cosine t minus t sine t. All right, but this is a function, and we were looking for the equation of a tangent line at this point. So I guess what we need to do is figure out what t value is this, right? To evaluate that, we need to know the slope of this particular tangent line, so we need to evaluate this dy dx function, but to do that we need to know what t value to plug in. Well, we have the point pi over 4 comma pi over 4, so pi over 4, that's the x-coordinate of the point, but the x-coordinate is given by t cosine t, and the y-coordinate of the point is pi over 4, and the y function is t sine t. So what we need to do is take these two equations and solve them for t. Now in general, solving an equation where we have t both inside a trig function and outside a trig function is usually impossible. But for these two equations, there's actually a trick. What we can do is take the second equation and divide it by the first. So on the left-hand side, pi over 4 divided by pi over 4 is 1. And on the right-hand side, sine divided by cosine is tangent. So we get 1 equals tangent t. And so t is pi over 4, possibly, right, because of the periodicity of tangent, we might have to add some multiple we might have to add some multiple of pi here. But to get these functions to produce pi over 4, actually, we don't need this extra k pi here. So the t value that we're after is just pi over 4. So now we can take dy dx, which is a function of t, and evaluate it when t is pi over 4. So sine of pi over 4 is root 2 over 2, plus t is pi over 4, times cosine of pi over 4, which is root 2 over 2, over cosine pi over 4, which is root 2 over 2, minus t, which is pi over 4, times sine of pi over 4, which is root 2 over 2. Okay. And then I guess maybe we should multiply the numerator and the denominator by 8 just to simplify all the fractions. So then we get 4 root 2 plus pi root 2 over 4 root 2 minus pi root 2. While we're at it, why don't we divide the numerator and denominator by root 2 just to get rid of that square root of 2. So we get 4 plus pi over 4 minus pi. And that's the slope of that line. So this is actually positive. Positive? This is... Why'd this come out to be positive? This shouldn't come out to be positive. I guess it could. So if we zoom in, so it doesn't actually look like this. This point, as we spiral like this point must be just below the right-hand point like this, so that this is a pretty decent-sized positive slope. So originally I had it drawn as if it was up there, but it can't be up there. It must be down here. Because this slope, 4 plus pi, that's about 7, divided by 4 minus pi, that's less than 1. So this slope is at least 7. So, it has to be pretty steep going up. All right, so now we have a slope. And remember, so the slope of our tangent line is 4 plus pi over 4 minus pi. And the point, we have a point on our tangent line, because that's pi over 4 comma pi over 4. And so now we can write the equation of the tangent line. We can use point slope form. So y minus pi over 4 equals the slope, which is 4 plus pi over 4 minus pi, times x minus the x-coordinate of the point, which is pi over 4. So there's the equation of the tangent line. All right, so the sort of the big picture here is if you want to solve some sort of geometric problem involving a parametric curve, forget that it's a parametric curve, right? Here what we needed to find was a slope. And to get started, forget that we're dealing with a parametric curve and just write down what you need to calculate. What we needed to calculate was dy dx. Once we had that written down, then we rewrite this in terms of t. And that was the tricky part, but we'll see some more examples. All right, here's another sort of geometry problem we can solve. So for what t values does this graph have a vertical tangent line? So this is all about the direction of the tangent line, right? And the direction of a tangent line is determined by the slope. So again, we need to work with the slope of this parametric curve, and slope is dy dx. Okay, but dy is dy dt times dt, and dx is dy dt times dx dt times dt. Again, the dt's cancel, so for any parametric curve, dy dx is going to be dy dt over dx dt. So let's calculate these. So dy dt is 1 minus 2 sine t, and dx dt is 1 plus 2 cosine t. Okay, so here's the slope of the tangent line. To find a vertical tangent line, this slope must be undefined, right? If this slope ever gave us a number, it's not talking about a vertical line. So we want to know, when is this undefined? Well, it's undefined when the denominator is 0. So when 1 plus 2 cosine t equals 0. And this is an equation we can solve. So let's move the 1 to the other side. 2 cosine t equals minus 1, and then divide both sides by 2. So cosine t is minus a half. And then write down all solutions for this. So t is, let's see, the principal solution is, looks like it's going to be minus pi over 3. But because of the symmetry of cosine, any solution, we can switch the sign on any solution and get another solution. So it's not, I'm sorry, it's not minus pi over 3. It's 2 pi over 3. There we go. And then so if we find any solution, we can flip the sign and we get another solution because cosine is even. But also we can add any multiple of the period, so plus 2 pi k. So this is all t values where the tangent line is vertical. So just to plot a couple of them, so 2 pi over 3, that's going to be the first positive t value. And if you look at these coordinate functions, right, when t is 0, we're starting here. So this is t equals 0. And as t increases, we're moving to the right. So the first place where we have a vertical tangent is right there. So this is where t is 2 pi over 3. And then the first place in the negative t values where we have a vertical tangent is right there. So this must be t equals negative 2 pi over 3. And then if you add 2 pi, you get this one. And then add another 2 pi, you get that one. And then starting at this one, if you add 2 pi, you get that one. And then the next one up. And if you subtract 2 pi, you get this one down here. So you can see we've found all of the places where there's a vertical tangent line. Another problem that we can think about with a parametric curve is finding a second derivative. So the second derivative of y with respect to x. Now this is going to be a little trickier because the second derivative of y with respect to x. One way to write this would be the derivative with respect to x of dy dx. Okay, and the tricky thing about this is it might be tempting here to write dx is derivative of x with respect to t times dt, but it's not clear what having this in this denominator, what that even means. But there's another way to think about it. So derivative with respect to x, the chain rule says the derivative with respect to x is the derivative with respect to t. Sorry, the derivative of t with respect to x times the derivative with respect to t, right? The chain rule essentially says that if you write down some derivative-looking fractions that look like they simplify, they do actually simplify. That's really what the chain rule says. So, so what we can do is replace this derivative, d dx, with this expression. Of course, derivative of t with respect to x, we'd have to know t is a function of x, which we'd probably rather not have to do, because often, x as a function of t is not an invertible function. But the inverse function theorem for derivatives says that dt dx is the same thing as 1 over dx dt. Okay, so what we can do is take this expression and use it in place of d dx up here. So now what we have is 1 over derivative of x with respect to t times the derivative with respect to t of dy dx. All right, so 1 over derivative of x with respect to t of the derivative with respect to t of, remember that dy dx, in terms of t, that's dy dt over dx dt. Okay, so now there are sort of two ways to go about this. We can either start computing derivatives and plugging everything in, or we could use the quotient rule to take the derivative of this quotient here. I don't know, I guess it depends on which one seems more appealing. Kind of depends on whether you prefer doing things exact and symbolically, or whether you like having sort of concrete formulas and functions when you're working something out. And it's usually a good idea, just for practice, to do the one that looks harder. And doing it symbolically seems a little harder, so let's do it that way. So 1 over dx dt times, so now we have to do the quotient rule here. So the quotient rule says derivative of the top, and the top is dy dt. So the derivative of that with respect to t is second derivative of y with respect to t times the denominator, so that's dx dt, minus the numerator, so dy dt, times the derivative of the denominator, so that's the second derivative of x with respect to t, divided by the denominator squared, so dx dt squared. All right, now if you look at this, there's actually another factor of dx dt in the denominator, so we get second derivative of y with respect to t times dx dt minus dy dt times second derivative of x with respect to t divided by the derivative of x with respect to t cubed. Okay, so now we can actually start computing some derivatives. So x is e to the t. So the derivative of x with respect to t is also e to the t, and the second derivative of x with respect to t is also e to the t. All right, for y, y is t squared minus t minus 1. So that means dy dt is 2t minus 1, and the second derivative of y with respect to t is 2. And now we can plug everything in. So second derivative of y with respect to x is, so second derivative of y with respect to t, that's 2, times dx dt, that's e to the t, minus dy dt, that's 2t minus 1, times second derivative of x with respect to t, that's e to the t, all over dx dt cubed, so that's e to the 3t. And then we can simplify this, right? We can get rid of a factor of e to the t. So 2 minus 2t minus 1 all over e to the 2t. And then we can combine like terms, I guess. So 2 plus 1, so 3 minus 2t over e to the 2t. And this is the second derivative of y with respect to x. Okay, so this tells you the concavity of the graph of the parametric curve as a function of t. Is that everything we were looking for? Okay, we wanted this when t was 1. So now we can just evaluate this when t is 1. So 3 minus 2 over e squared. So 1 over e squared. And we're done.